let's do exercise 66 together as an example of a further example of proving some things involving domain. And I like this one because it incorporates union, which is another thing we recently learned about. So we're going to prove that if S and T are both sets of pairs, then the domain of their union is the union of their domains. So before we start the proof, actually, I want to, let me remove the word proof here while I do this. I want to just think about why would we imagine that this is true in the first place. So if S and T are sets of pairs, that means what I imagine is that each of S and T is a box, a collection of things. So each one is a container. And when I say set of pairs, I mean everything that it contains is a pair. So it contains all these pairs, which I imagine is these parentheses with comma things, with each pair is a first position and a second position. And T is a bunch of pairs. Then what does it mean to take their union? To take the union of these two boxes is basically to merge them, right? So it's like taking the union is like removing the wall of the container and then merging it into one container. And then you might have some repeated things that were in the intersection would now be repeated, but you just ignore repeats since sets cannot give you any information about repeats. So that's the idea of the union. Now, if you take the domain of something, a set of pairs, then what you're doing is you're collecting in one set all the first positions, right? So what it says on the left-hand side here is first take the union. To form this left-hand side here, first take the union. So first do this. Then you'll have S union T. Then take the domain of that. So then collect in a box all of these things that you find here in the union. Collect all of those together. So that's what the left-hand side says. On the other hand, the right-hand side says, first take the domain of S. So collect all of these together into their own box. So put all of those, throw them into their own box, and call that box domain S. And then collect these together into their own box. That'll be called domain T. And then union these two boxes together. So merge these two boxes afterwards to get domain S union domain T. So that feels like it should be the same. In other words, those two operations should commute, taking domain and taking union. Well, let's prove it. So this is an equality, so there'll be two inclusions. So let me write things out in a nice level of detail. You know, sometimes I just do like this, headings like this. That's just being lazy. It's okay to do that, since using theorem 10, using this idea that equality is double inclusion, that's so standard, so popular of a thing to do that everyone will understand what you mean if you just do this. But let me not be lazy this time. All right, so I've got these two subclaims to prove, one inclusion and the other inclusion. Domain of union is contained in union of domains, and union of domains is contained in domain of union. One reason I'm choosing not to be lazy this time around is just to suggest to you a way of organizing proofs, since some of your proofs coming up are going to get a little bit longer or more complicated. It's nice to know that you can organize things into claims and subclaims, and maybe within the subclaims you have more subclaims. That's all fine. So I'm going to also show you, although we don't need it here, that you can number your subclaims. You don't have to, but it helps for if you later want to refer to something like, oh, this is by subclaim 7, which we proved 3 pages ago. Hopefully you never have to do a proof that long in this class, but this is a way of organizing things. Okay, so when I give this a heading like this, it has its own proof. So these have their own proofs. Okay, let me move subclaim 2 out of the way for now. All right, let's see what we can do with this. So I'm trying to prove this inclusion, so I have to use a universal generalization kind of argument, since this inclusion is saying every element of this is an element of that. So consider any, let's call it z, in the left-hand side. Now, to get anywhere, there are a couple of things I can do here. I can start by unpacking what I've got, or I can switch to focusing on my goal, which is to show that z is in there, and then unpacking my goal. Remember that when I'm unpacking what I have, I can do that straight in the proof. When I'm unpacking my goal, usually we don't do that in the proof, because it's not clear. Usually it's not clear what's the right way to unpack the goal. Sometimes there's more than one way to do it. But also, if you stick it in the proof, there's a danger of writing things backwards, or, you know, accidentally asserting that your goal is true before you actually reached it. So if you include unpacking your goal in your proof, you have to make sure you use very clear language to point out that you're not saying this is true yet. You're saying this is what you want to prove. So, for example, I wouldn't write, this is something I've seen people write in the class so far, writing something like, then z is in domain S union domain T. Like, no, this is what we're trying to prove, right? I get when someone is writing this, they're trying to say, then we want to prove that this is true. But there's a very big difference between saying you want to prove it's true and saying it is true. Okay, I'm going to start by unpacking this. So this says, just using axiom 5 in the definition of domain, it says that there exists a y, right? So the domain is the set of first positions of pairs of things in there, right? So this is saying there exists a second position. There exists a y such that this is in there. Oh, sorry. In there. So we can now apply existential instantiation. So, we can get a y such that the pair zy is in S union T. Now, usually what people will do is they will sort of use axiom 5 implicitly without explicitly writing everything down every time they use it. So the transition sort of from here to here, like from this to this, that will just get skipped over. Like people will say z being in there is this statement. So axiom 5 is considered so close of a link between this and this that people will not even write this second one. So here's what you will typically see, and you're allowed to do this, although you don't have to, is this part will be skipped. And you'll just go right to this. So this is an existential instantiation, going from z in the domain of this thing to we can get a y such that the pair zy is in the thing. That step is still an existential instantiation. It just skipped the part where we explicitly write down the existential quantifier symbol. So you can do this, but be aware that all of the usual rules of existential instantiation apply. So for example, this y that we can get here has to be the variable you use for this y here can be any variable that you have not previously used for something else. All right, and now I've got something in a union, so I can use the definition of union to unpack that. So then zy is in S, or it's in T, which gives me a case split. So there's case 1, and case 2, zy is in T. Okay, so in each case I want to get to victory. What does victory mean, though? my goal from the very beginning was to prove that my z is, that my z is in the right-hand side set here. So maybe it's time to unpack the goal. Let me go off to the side for a bit and give myself some space here to think about my goal. So what I'm writing now is some scratch work. And I know I'm putting a lot of the work here out of your view, but you can see here I'm trying to show that z is in there. So my goal is prove that z is in there. The union of the domains. So unpacking that means I want to prove that z is either in the domain of S. So I have two ways of reaching the goal. Either prove z is in the domain of S, or prove z is in the domain of T. Those are two paths that I can take to reach the same end goal, which is z is in this union. So if I want to take this path to do it, then let me do it this way, i.e. either prove z is in the domain of S means prove there exists y such that the pair zy is in S, or prove z is in the domain of T means there exists a y such that the pair zy is in T. So I'm either trying to prove this existential or that existential. How do you prove an existential? Okay, we've been there before. We were just there in the last video. You use existential generalization, which is a fancy way of saying find. So either find a y such that this is true, or find a y such that this is true. So now I've really broken down my goal and I see what I need to do. There are two ways I can reach the end. Either I find a y such that this is true, because if I do that, then I will be able to existential generalization my way up to z is in the domain of S, and then that will allow me to conclude pretty quickly that z is in this union. Or find a y such that this, and then there's another path. So you see how if I don't break down my goal, this would have been pretty hard to see what to do next. It's okay to do this in your head if you can. I mean, when you've done this enough, you can probably do this stuff very easily in your head. But right now, I would definitely do it on paper. Okay, back to the proof. Now, one thing that I'm noticing is that in the proof, I'm already using y here. I'm already using the letter y. And yet in my goal description, I'm saying find a y such that blah, blah, blah. So the y is sort of bound by the existential quantifier here, which means I'm biasing myself into thinking that it's going to be the same y that's over there. Actually, it is going to end up being the same y, but it didn't have to. So let me not use y here. You know, what was previously written here before I erased and changed things was an existential quantifier. There exists y. So I could use any variable there. And I'd rather use a variable that isn't one that's already in use. So I'm going to say find a, let's call it, not z, what's a good letter? E? Find an e such that the pair ze is in there. Or find an e such that the pair ze is in there. And the e could be anything. Yeah. Okay, so keep this in mind as we look at the proof. That's my goal, is to find something such that when I put it in the second position, z comma that something is in S, or z comma that something is in T. So here we are in our proof. We're in the case z comma y is in S. Oh, we already reached the goal, right? Y is that something. So if z comma y is in S, so now I'm just climbing back up the goal stack. So you see, by breaking down my goal, I sort of worked backwards up to the point that I'm at here. So then there exists a y such that the pair z comma y is in S. So this is the existential generalization, is straight from the case assumption. So z is in the domain of S. Therefore, z is in the domain of S union the domain of T. Now, really, so if you're still doing some homework problems where you're proving elementary facts about unions, this would be an unacceptable jump. You have to use the definition of union to go from here to here. Or you have to explicitly reference Theorem 31, which is actually what I'm using here. Specifically that, if you're in the first thing of the first part of a union is a subset of the union itself. So if something is in here, then it's in here. But since this is much further along in the notes much further along in our theoretical development than back here, I'm allowing myself to freely use this without reference. But maybe I should put the reference. By theorem. It never hurts to put a reference. And it sometimes hurts to not. 31.1. Okay, and then this next case is going to be pretty similar. So I'm going to copy and carefully read through and make sure it still works and make the changes where needed. So I'm assuming that's true, then this is a T. So this is a T. And then this is now by theorem 31.2. Great, so in both cases I reached my ultimate goal of z being in there. Now let's look at subclaim 2, the other inclusion. So consider any z in the left-hand side. So I have something in a union. By the definition of union, that means either z is in there or z is in there. So I can say that, or we're used to it enough now that I can just immediately go to the case split. Case 1, suppose that z is in there. Case 2, suppose that z is in domain T. Okay, now in each case, I want to get to the ultimate goal of z being in the right-hand side here. So starting with case 1, let me unpack this, and then I'll go think about what my goal amounts to. So suppose z is in there, then. So I'm going to show you again how we can, how to write things out fully versus how to skip that one step where you write the existentially quantified statement. And both are okay. So if I write things out fully, what it means for z to be in there is there exists y such that z comma y is in S. That's applying axiom 5 to this membership statement. So we can get, now existential instantiation, we can get a y such that this is an S. And then if you want to skip this sentence, then that's okay. Now let me break down my goal a little bit more talking, kind of doing it in my head rather than writing things down this time. So my goal is to prove that z is in here, right? So that means, by definition of domain, to prove that something is in the domain of something, to prove that something is in the domain of a set, I have to prove that it, comma, something else as a pair is in the set. So I want to prove that z, comma, something is in here. So that means my goal is to find my goal is to find something, excuse me. So my goal is to find something such that z comma that something is in S union T. Well, I have something such that z comma that something is in S. And S is a subset of S union T. Again, thanks to this idea about unions. So I'm already almost there. So the correct next thing to say is then this is an S union T by the theorem that says that S is a subset of S union T, so 31.1. So existential generalization, that means there is something such that z comma that something is in S union T. So z is in the domain of S union T. So that's again axiom 5 applied to this membership tells us that it's equivalent to this. Okay, and I'm going to copy and paste for the next one. And just carefully read it and make sure everything makes sense. So z is in domain T, so we can get a y such that, and then this should be a T now. And then this will be by theorem 31.2, which tells me that T will be a subset of S union T. And I think this line is fine. So that's it. And now we have proven that the domain of a union is the union of the domains. Now, one thing you may have noticed I never did is I never made the assumption that S and T are sets of pairs. If you look at exercise 66, which I've copied down into this claim, it's an if-then. If S and T are both sets of pairs, then this is true. But how come I never assumed the hypothesis of this if-then? Why isn't my first line assume that S and T are both sets of pairs? Well, I could make it my first line, but I never needed that assumption. So actually, a stronger statement is this. This is simply true. So sometimes this happens when you come up with a conjecture which you then go try to prove, and your conjecture has a bunch of assumptions. If all these things hold, then this holds. And you end up in your proof not having to use some of the assumptions. Then you can go delete those assumptions from your theorem statement and get a nice, stronger theorem. But typically, you would only ever talk about domain and range in situations where you're looking at a set of pairs. So let me go to the definition here. If you look at the definition of domain and range, the definition does sort of seem to require that you'd be looking at a set of pairs. But in this case, that definition is just there. That requirement is just there to suggest to you the typical context in which we would use these definitions. If I delete this, let S be a set of pairs, it does not harm anything. You can still use this definition, and we can still prove this even without assuming S is a set of pairs. This is in stark contrast to the definition of occupant, where it's required that S be a singleton. So yeah, you can delete this, let S be a singleton, and then still make this definition, but you're going to miss out on being able to use essence of occupant. And if you can't use this, then the whole construction is not that. The construction is not serving its intended purpose then. So sometimes definitions come with assumptions, and in some situations those assumptions are needed to make the definition operate in the intended way, and in other situations like this one, the assumptions are suggesting to you or building up a context in which one would typically use the definition. I guess those are pretty similar things anyway. So one other comment about set of pairs. This is something I have not discussed that much in lecture, but it's there, and you should hopefully you're looking at it when you're reading. So it's in definition 40. To say that a set is a set of pairs which is also sometimes called relation, is to say that every element is a pair. So when someone says S is a set of pairs, they are saying all elements are pairs. So for all, this is a lowercase s, for all little s and big S, little s is a pair. So this is what it means to say that something is a set of pairs. And then is a pair is also defined here. So we say a set is a pair, if it has the form of the pair. So this is a lot like earlier, the idea of being a singleton. A set is a singleton if it can be written as singleton x for some x. So it's an existential kind of thing. To be a pair means there exist A and B so that you end up being equal to the pair AB. So S is a pair. This can be expanded like this. S is a pair is there exists AB such that S equals the pair AB. So this overall here is what it means to say that capital S, sorry, I should make my capital and lowercase s's look very distinct. So my lowercase s is a little bit cursive looking. Okay, so this statement here is what it means to say a capital S is a set of pairs. Every element is a pair. So what do you think about the empty set? Is that a set of pairs? So pause the video and come up with a guess. Okay, so my answer is yes. It's definitely a set of pairs. Because this ends up being vacuously true, right? Every element of the empty set is a pair because it has no elements. So this implication is always true for the empty set because the hypothesis is always false. If you put the empty set in place of capital S here, then this is just true because the hypothesis is false. Another way to put it is, indeed, none of the elements of the empty set are pairs. How about, oh yeah, so that means one totally could talk about like the domain of the empty set. What would the domain of the empty set be? So take a guess. And here's my answer. So thinking intuitively, the domain of the empty set should be the collection of all the first positions of pairs that are in the empty set. But there are no pairs in the empty set. So we just get the empty set. But this should be something that you could prove if you wanted to using the original definitions. How about a set that looks like this? Is this a set of pairs? Well, you don't know. I mean, to say that this is a set of pairs is to say that every element, so x and y, is a pair. But we don't know much about x and y, right? So maybe they are pairs. I don't know. Okay. What if I did this? Is this a set of pairs? So a good first answer, which is not quite correct, is no, it's not a set of pairs because these are doubletons and not pairs. So this overall looks like it's not a set of pairs. The elements look like they are not pairs. But to really prove this is not a set of pairs, you would have to prove that for at least one of these elements, so like this one, that it is impossible to write it as pair AB. That it cannot be written like this for any AB. Can we really prove that? I mean, after all, ordered pairs are certain kinds of doubletons. That's what they ended up being. So actually, even in this situation, it's not clear that this is not a set of pairs. Can you think of something that is not a set of pairs? So can you think of something that is definitely not itself a pair? I'll leave you with that to possibly think about.